Hi, my name is Ken Hao. In this video, I'm going to present about a project called Finger Control Detection Algorithm using Deep Learning with Brain-Computer Interface. In this work, there are four ways on how people interact with computers. They are the keyboard, mouse, touchscreen, and voice control. If you look at what is common between them, you'll find out that all of them requires the physical interaction of the human, and the results are not instant. But if I tell you that there's a way to interact with computers without the need of any physical movements and the results are almost instant? The answer is interacting with computers directly through our thoughts. If we can do that, we can change the way people interact with computers in their daily life. Besides, we can also help numerous people in healthcare. For example, this can be applied to rehabilitation for the stroke patients, as a communication device for people who lost the ability to speak or write, as well as to control the prosthetics for the people who have lost their limbs. This is also the reason why I choose to develop in this project, because it can help numerous people. Now we have a big picture on how this project will contribute to a society. In order to achieve that, we are going to start small by developing a brain signal detection system based on deep learning. Before I going further into this project, let's discuss about some terms that will be widely used in this project. The first one is the BCIs, Brain-Computer Interface. BCIs are devices being used to detect the brain signals from human brain. There are three types of BCIs, namely invasive, partially invasive, and non-invasive BCIs. The main difference between them is that invasive and partially invasive BCIs requires the clinical surgery to implant the sensors into human brain, while non-invasive BCI does not require such process. Because of this limitation, this project is going to use one type of non-invasive BCI, which is the electroencephalogram, EEG. EEG works by detecting the brain signals in terms of voltage fluctuations. Due to its non-invasiveness, it does not pose clinical risk to the user. Besides, it is relatively low in cost. That's why EEGs are almost affordable to everyone. Another term that I would like to discuss is the motor imagery, MI. Motor imagery is the imagination of body movements or the motor movements. In this project, we will be classifying the motor imagery for the 5 fingers. Why do we choose to start classifying in motor imagery for fingers? The reason is fingers are the body part that can do the most complex movements. So if we can classify these movements, we can easily modify our project to classify the other movements from different body parts. There are 3 major steps on how this project works. The first one is to collect the brain signals dataset from the user performing the motor imagery. After collecting the dataset, we will feed the data into a deep learning algorithm. Right here, the algorithm will try to learn the patterns that are associated with the brain signals. After learning, we will perform the test on the learned model on classifying these brain signals. You can see that this is the entire hardware setup required for collecting the dataset. So this one is the Open BCI EEG headset wearing by a subject, and right now he's performing the motor imagery for right hand fingers by following the video instruction shown on the screen. Coming to a deep learning algorithm in this project, the algorithm is being developed by using the MATLAB software. The picture in the middle shows the training progress of the deep learning models. And the bottom right here is the illustration of the neural network models being used to classify the brain signals. In this project, We have experimented with 4 different techniques to classify these brain signals. Because of the time limitation, I'm not going too much detail into the technical aspects for this project. We have tested the outcome of this project in 6 subjects. They are different in terms of the age, gender, as well as their occupation. Coming to the testing results for this project, we have obtained the best average accuracy of 82.83% and 69.0% for classifying 2 classes and 6 classes respectively. Because of different number of classes being used, we must compare them by using the kappa score. From a previous research, the best kappa score that we can obtain is from the Ganoni et al. In their research in 2020, which is the kappa score of 0.76 and the level of agreement of good. Our results are slightly lower than this research, but we are in the same level of agreement. Besides, if you notice that when we change the number of classes from 2 to 6, the kappa score only decreased slightly. This means that we can modify the number of classes in this project without losing much performance. This project has successfully created the classification algorithm to classify the brain signals associated with motor imagery for finger movements. The outcome of this project are with great classification accuracy. Besides, we are currently further developing this project to classify and control a hardware in real time. By starting small and building up this technology bit by bit, we truly can change the way people interact with computers. And we can help lots and lots of people in their daily lives. If you wish to know more about the technical aspects of this project, feel free to contact me through email. That's all for this presentation. Thank you.